Hello Internet! Welcome to Fun Project Monday, this time actually on Monday. I'm Kaffee Apparat, you can also call me Robin. And this is the engineering live stream. We build stuff while relaxing. Let's start with some coffee. Wow, shit. That was good. So, we are still in the conception, in the defining stage of our desk-mounted LED desk controller thing. Yes, that's the correct term. And last time we did some sketching, some basic outlining what we actually wanted to do. Today we'll do some calculations. Unfortunately, Murphy has taken its toll and the stuff from last time wasn't saved. So we'll start a new document. Who cares? And we said that we wanted to have 3 LEDs or 3 channels, 3 LED striped channels. And now we need to somehow estimate how much current or for how much power we will need to design our product. Yes, let's start. For this, let me change something. Not here. This one, yes. For this, I opened 2 sites. You can be pretty sure that most of the LED strips you are able to get will be the same. So, for the 12-volt ones, we will most likely having 14.4 watts per meter and with 60 LEDs. And with 30 LEDs per meter, we will have 16.5 watts. Because that were the first 2 images or the first 2 sites I got. And I will check that value. Why? Why should we check such values? Or why should we check if we bought something or if the calculations or the numbers that our distributor gives us, if they are correct? To see what kind of formula they used. In mechanical engineering, we also did that. So we got some data sheets, and then we figured out what kind of formula they used and did calculate it ourselves to get roughly the same estimates. And we're going to do the same here. For that, I will change. So for the 12 volts with 30 LEDs, let's see, change something here. Otherwise, it would look pretty awkward. So with 30 LEDs, of course, I always take the best way to write LED. We were working with 6 point, you can see my face. We are working with 6.5 watts per meter. That means for that we can check the formula. Like, it's actually very simple. We have the LED count times the number of sub LEDs. In this case, it would be 3. Now, let's write it out. Times the LEDs per meter. And of course, the voltage we are using. Not count the LED current. If we put the numbers and we'll see, okay, the LED current is in most data or most traders and distributors don't give you that value. So we can, of course, do some basic, what do you call it in English? You could change the formula, so that's what, and we divide through it so that The LED current would be the sub LEDs times LED per meter times voltage divided per watts. Yeah, I won't write it down. It doesn't matter. Either way, for the 12 volt strips, we'll get 0.7 milliamperes per sub LED. And if we put all of that in that formula, we can get to the actual amount 6.5 watts rough estimate. We do this because when we could decide if the 60 watt LEDs or the 60 watt strips were our LEDs built in, or they're using other kind of resistors or whatnot. But with that, we can actually check that in the 30 LED strips and in the 30 LED per meter strips and the 60 LED per meter strips, the LED current is the same. Let's do this. Oh no, let's write that down. That's okay. So we have 0.07 ampere times 3 times 30 times 12, and that should give us 7.56 watts, or was it 0.65? No, it was 6 milliamp. Of course, I've completely written it down falsely. And I use, of course, that would be very bright LEDs. If you would have used 60 milliamperes, that around 6.48. 6.48 watts. The same we will get with the 60 LEDs per meter. And the formula is the same, except we use 60 instead of 12 volts. So with the same formula, we get to roughly 14 watts, which is actually the same that the datasheet is giving us on the trader. For the 5 volt strips, I had an example and I checked it with a power supply. So we have actually, how much was it? 30 milliamp, 10 milliampere per LED, at least in the specific strip I got. And with 10 milliamperes per LED, so 1.01 ampere times 30 times 3 times 30 times 5, we get to round about, let me check, 5 watts per meter. 5 watts. We did this ballpark calculation, first of all, to check if everything makes sense. And now we can actually decide how much LED strip we want to drive. In the first live stream, I didn't specify how much LED strip we want to drive because I wanted to see, okay, how much power does a LED strip actually draw. So for the 14 watts, that would be round about 1 ampere per meter. And if you check supply and availability, it is most easy to get 3 to 4 ampere switching power supplies. So that's the next point. What kind of power supply and power supply structure do we want to use? Because that is all entangled with each other. So let's take a look. There are 3 basic layouts we could use. Let's take a look on that. So in every case, we have our voltage in. Then we got our DC-DC converter that converts the 15 or 24 volts or whatever you want to use to the 12 volts that we are interested in, or the 5 volts that we are interested in. And then we fuse each, that's actually very nicely drawn. And for everyone not knowing, this is the symbol for DC-DC converter. So you want to fuse each of our LED, 3-channel LED strips separately. Yes, that looks very good. To our 3 channels. So we have here channel 1, channel 2, and channel 3. Of course, that design brings a lot of implications with it. First of all, we will need to build a massive switching regulator. Very interestingly, they are pretty available currently. On DigiKey, I found a part which is rated for 10 amperes, 12 volts, for $1.80 in single quantities. That would be a very good fit for that application. But of course, we also have to look for all these fuses, and we would need to have very thick traces transporting the current through the board. So maybe that's not the optimal design. And for our design goal of having an optional 5 volt LED strip support, it is not very optimal either, because we will need to add another switching power supply and the power chain, and we want to avoid that. Let's take a look on the second possibility to design such a device. So you have a single DC-DC converter. Of course, we could use two DC-DC converters. Having the, I will write it down, 2 DC-DC. That would have application. It will look like that. So. Yep, I can't decide where around I want to draw this. So let's keep it consistent. So we have here 12 volts. Add it here above 2. And down there we would have a 5 volts. So we have them in parallel, and we are driving both of them at the same time. Of course, for every channel, you would have a selector MOSFET to change between the 5 and the 12 volts. So it would look like something like this. When you have some sort of switch, and then we go to channel 1 and channel 2, and so on and so on. Of course, that design would imply having, actually it's the same above, but with a 5 volt converter actually wrote down. Then I have 2 more for you. The second would be we use 6 DC-DC converters, yes. There is one very big advantage to using multiple DC-DC converters, each for each channel. DC-DC converters most of the time have a shutdown feature. So they, not a shutdown feature, but a short circuit detect. So if we have an overcurrent, the DC-DC converter shuts down by itself, And we don't need to fiddle around much with fuses because the DC-DC converter already does it for us. So that would be a very good idea in that regard, but we'll see why it is actually not a good idea. 6. So we still have our 5 volts in, or our voltage in, or 15 to 20 volts, and then we go down. And then have one channel using the same. So. And of course, still the switch. And then you have channel 1, and so on and so on. I won't draw it all up. The implication of such a design would be that we drive most of the converters at almost the maximum output current they can output. This is of course not that good because with the higher output current, the efficiency goes down a little bit. With such designs like above here, we could get better efficiency as long as we don't use all the available current. But here we have the big, of course we need to fuse those, yes. Of course we would need to fuse every one of them separately. With this design, we can get rid of the fuses, maybe have one fuse at the input. That is actually always a good idea. And we are able to, like I said, use the shutdown feature of the overcurrent feature of the DC-DC converters. Of course, if you use 6 of them, they will take a lot of space. If you take one of these voltage control, these buck boost converter modules, now they're only buck or boost converter modules, they are relatively spacey. And if you have a very small or relatively small desktop device, maybe that's not a good idea. Another option would be we use only 3 DC-DC converters and have both voltages. And I think that would be the best idea, and I will show you why. So using 3 DC-DC converter, TUS. So let's write this up. And then we go directly to channel 1. And we're doing this with the other channels too. And of course, the question is now, okay, Robin, you told us that's not a good idea because, or using single DC-DC converter for a channel, because we can't change the voltage. But we can. We can do this pretty good because if we use an adjustable DC-DC converter, we have some kind of feedback loop. So we will have our IC here, or our switching or DC-DC controller IC, and some of the current will come out. So we have the out. And those adjustable DC-DC converters have a feedback loop. So there is a resistor, and then there's another resistor. And this feedback sets the actual voltage at the output. And that goes to ground. What we can do is we can add another resistor in parallel and use a MOSFET or use some kind of switch. Let's draw it as simple as possible to change the voltage accordingly. The big, I'll do it in another color because it's, yeah, I'll do it in another color. Can you do this? course I can do that. So we'll add this path here. Oh my god, does that look good? So we have electronically controlled electronically controlled DC-DC converter, where we can switch the voltage between 12 and 5 volts. Yes, and I think that would be a good solution, to use 3 DC-DC converters with such and switch. I had another idea, which came to me yesterday. I said that it would be a lot of hassle to add support for digital controlled 5-volt LEDs. I came to the idea, actually it's not that hard. I will tell you why. Because we will have a switchable power supply so or so. So we'll have 12 or 5 volts at our pin. Digital RGB LED has a following pin out. So there's some kind of, so that's our LED. It has plus 5 volts. This has a data line. And it has a ground line. With those 3 pins, we can drive the LED. Of course, the 5 volts goes to our voltage in, or voltage out in that case. Ground goes to ground. Now it's the question, how can we implement the data line? The data line is a digital signal which gives out some values. And what we could do, instead of saying this is an... to make it more clear, I will add, this is our controller. And it would have the pins 1 and 2, 3, 4 for RGB. The way that the 12 volt strips is that you short or that you connect either the R or the G or the B pin to the ground to get the desired color. So we could use one of these RGB pins to simply connect inside to ground, and we could use another of that pin with a high side switch. So we'll draw it very easily, very simplistic again. We will need a resistor too. So we use a switch and a resistor to supply the 5 volts or 5 volt signal to the data pin over one of the RGB pins, for example R. So we only need to keep the right pin out at the connector in mind. And then we can use microcontroller. So this is connected and this is connected too. And then we can use a microcontroller in some way to toggle the voltage on that pin to deliver the right data output. And that is something which is, I think, very elegant and that I will implement because it looks pretty nice and it adds a lot of capability to our device. So with these thoughts, I will leave you. Have a nice day and take care.